Before we start, a great thanks to all the organizers. I don't see them around now. Maybe they're still downstairs around lunch. Thanks to Leah, thanks to James. I know how much is involved when you try to organize such a conference. We have our own conference next week, and this is really kind of work. There was a time when I thought this is just, you do a conference or something, but this is really work. So thanks a lot for making this happen here in New York once again. For all those who are interested in the material, especially the slides actually, I have put together a list of links on my web page, hilpisch.com. You see it over there. I hope you can read it. Where you find a link to the slides, a link to a GitHub repo that I will mention, documentation, and a couple of others. I'm founder and managing director of the Python Quant company. I'm from Germany, and the company is also located in Germany, but we have people here in New York as well. What we're doing is all centered around Python for quant finance. Actually, I'm running a large meetup group in London, for example, where we have 400 people right now, which is completely focused on Python for finance. We, for example, have a workshop in December, which is completely dedicated to Python for Excel, where we have 3 people who have written nice libraries to integrate Python with Excel, giving a workshop. So we have many activities, and the group is really active over there. Ian is here. He hosted us once with Pivotal. Thanks for that. We have also, and James, this is one of the many activities that James is involved, a Python for Quant Finance group here in New York. Not yet that active, but we're working on that. So if you're in a finance space using Python, you might have a look at the group as well. Next week we will have our For Python Quants conference in London. The second of its kind. The first was this year here in New York City in March on PyDay on the 14th of March with 225 people in attendance actually, 2 tracks. We're expecting a similar conference this year, or at the end of the year actually, in London as well. So you see everything is centered around Python and quant finance. But before I start, how many of you are from the financial industry? Oh, there are many of these. This is what I was hoping for here in New York City. It's not in every place. For example, my last talk that I've been given was in Dublin, Ireland. There haven't been that many people from the financial industry, but so there's no wonder that you're interested maybe in what I will present today. But let me start. The Python language. My talk is actually structured the following way. First, I will argue why Python is popular these days in quant finance, and secondly, how and what you can do with Python in this space. Let me start with the Python syntax, actually. The Hello World example of quant finance is the geometric Brownian motion of Black-Scholes. Back in 1973, they used it to derive for the first time an analytical closed form solution for the price of an option dependent on kind of a stochastic underlying, mostly interpreted as a stock or stock index. I'm not really interested in solving stochastic differential equations. Usually what we do is computational finance in the sense that we apply numerical methods like Monte Carlo simulation. And here is one option to discretize the whole thing for the purpose of Monte Carlo simulation. You see, I start with a S0, which is the initial value of my stock index, or whatever this represents. And via this discretization, I can simulate values at the end of the horizon, usually at the maturity date of a European option, for example, in this model. Details are not that important. The point that I want to make here is that whenever you have been studying finance or publishing scientific research papers or whatever, you might have come along LaTeX. Who of you have ever used LaTeX to write things? Yeah, the majority actually. And I think LaTeX should be expected to be pretty close to the mathematical formulation of equations, problems, or whatever. So once you want to translate what you've seen before, or actually this is the basis, I'm just showing here in raw text, the LaTeX representation of the Euler discretization is pretty close to the formula actually. So many people, be it physicists, mathematicians, finance people, they pretty quickly catch up with the language and are able to translate the mathematical formulae to the LaTeX description. But the point that I want to make here is that if you go one step further and have a look at Python, this is also pretty close to that. So from my point of view, these days, when I speak of scientific languages, it's usually English. Nobody publishes anymore in German. This was like 250 years ago. And this was kind of the standard scientific language, but not for long. These days, it's English, and of course, you have to know mathematics. And if you know Python and LaTeX, you're mainly done from my point of view. You see here the syntax is pretty close, and that's, I think, one of the reasons why people usually coming from a scientific background, scientists in a general sense, like to use Python because it's so close to what they usually already know. Even if you don't know it, I'm giving a lecture at university, and I have many people there who have never programmed at all, apart from a little bit of VBA and Excel, maybe. They can understand what's going on here because it's really pretty close to what the math representation of the problem, of the equation, is all about. But it's not only this, it's also the interactivity, especially when thinking of data scientists, as we call these people today, or the students that I was mentioning before. With Python, only a few lines of code, and this is not pretty hard to learn, suffice to kind of visualize the things that you're doing. This interactivity and to see something visualized immediately after you have been doing something is also something that makes the language pretty beautiful. I mean, you will find this in other places as well, but my experience is more often than not is not that appealing from a syntax point of view, and sometimes, or even more often than not, it's much harder to learn to do the same thing that you can do here in Python. The Python ecosystem for sure is the second point why Python has become that popular. I don't want to elaborate on that. I mean, the whole conference is about the Python ecosystem. I just want to mention a few things that I think make Python so appealing. Of course, we have the IPython notebook. You see my presentation is written in IPython notebook. It's translated afterwards in this HTML5 presentation. I did a little bit of tweaking with the CSS, but only a little bit. And that's the beauty of this tool. And I like to say these days I live in this tool set. My last book that I have written, the Python for Finance book for O'Reilly, is completely written in IPython notebook. A 600 pages book written in IPython notebook. NumPy, SciPy, Pandas, I don't need to go into details here. You're all aware of what the Python ecosystem has to offer these days. And then this might be one of the major points. And I've been with a potential client yesterday, a larger fund, more than 6 billion under management here in New York. They're not using Python yet, but they asked me, well, what's the major reason? Why should we start thinking at all about using Python? We have this and that and this and that. From my point of view, Python is pretty good when it comes to making no decisions, in a sense. There's no either or with Python. You can integrate with almost any other technology you're already using. There's no reason to say, well, I'm leaving this and going now over to Python and have to start anew. Python integrates pretty well, and I want to illustrate it by two brief examples. You might have seen these in other places and in different disguises, but I want to focus here from this list on R and Julia. Actually, what we all know, it also integrates pretty well with C, C++, and so forth. First example is statistics with R. This is actually a financial example based on a Eurostoxx 50 index and the VStoxx volatility index, and there's kind of this stylized fact that both indices, the same holds true for the VIX and the counter index, are highly negatively correlated, and we just want to replicate this result with using Python and R, a combination of both. What we do here is kind of we read data from disk into Pandas data frames, and just to see what data is stored in there, I'm plotting the closing data of the Eurostoxx 50 index over the last years, actually starting in 1987 up until recently. This is the data we have. What I do here in Python right now is to calculate the log returns over my Pandas data frames. Again, I don't want to go into the details. This is not a talk about Pandas. But of course, it is pretty appealing to calculate log returns here in this case in a highly vectorized fashion. You see it's a single line of code to do these operations over whole data frames. And in the same line of code, I also drop all the not the number values, and I end up with kind of a data set that I can work with. What I do here is kind of I define reference pointer, ES and VS, that I can work with afterwards. I'm only interested in the values from two selected columns out of my two data frames. Nothing more, nothing less, and there are the log returns stored in. With IPython and the extension rpy2.ipython, I can easily push these to R, to the R runtime. How many of you are using R alongside Python? Oh, there are a few. Not that many, but still it's kind of a usual thing that we encounter in financial companies, be it banks or hedge funds or whatever, that there are of course more technology than only Python. Or the other way around, more than R, no matter where you come from. It's pretty easy to push here my data to the the R runtime, and then I do only simple things here just to illustrate how easy it is. I plot the data using R because there's always this ongoing debate. Well, matplotlib is not yet good plotting library, and I like my R plots. Well, it's pretty simple to push the data over there and to get your R plot if you like that more, or if you can better cope with the R technology in that sense. We can do typical statistics like the linear regression. We can print summary statistics from within IPython using R. And in the end, we end up with this result, actually already supporting the hypothesis that both indices are negatively correlated. You see the linear regression line has a negative slope, and this indicates negative correlation. And well, maybe this is not the end of your analysis, and you want to use the results from the R runtime within the Python runtime. You can pull back the data again. Here in this case, I only pull back the regression coefficients of my linear regression, and I replicate the plot now with matplotlib. Not to say that this is better or worse. I mean, I'm used to this, maybe more than to the R representation, but to me, both look pretty similar. What is maybe more interesting is that you can use technology like the one from Plotly. Who's ever used Plotly in here? I'm so like, there's only a few. You might give it a try. Plotly is actually language agnostic. It works with MATLAB, with R, with Python. What I do here, I import the Python library. I sign in on the server. So what is happening now happens on the server. Actually, I pass data to the server. In this case, I sample down because if you're not running a Plotly server on your own server, then you have to transfer all the data. This is kind of a mess, of course, especially when speaking of big data. You don't want to transfer your big data to someone else to render your plot. Therefore, I'm sampling down it here a little bit. And what you see here, with a single line of code, I'm taking this matplotlib picture and get it back rendered in the 3 JavaScript, and you see this is completely interactive. And I can embed wherever I want to do it. This is now embedded in my IPython notebook. I can, for example, zoom in, but I can also embed this particular plot on a website or wherever. So it's a single line of code to get out of your matplotlib static plot an interactive JavaScript D3 plot that you can embed anywhere you want. So maybe this might be more appealing to some people who don't like matplotlib. The other example is working with Julia, one of the standard examples these days, of course. I don't want to go into the details. Here's the Fibonacci sequence. We all know that Julia is in many respects faster than pure Python. The point that I want to make here is kind of you have the iterative function formulation. You see it's much faster in Julia here than in Python, so it might make sense to use Julia from within IPython notebooks to do certain things. You see the iterative formulations are faster. These are much larger numbers that I'm using here. In both cases, but nevertheless, Julia, due to being dynamically compiled, is even much faster. But to bring justice, I mean, Julia is a dynamically compiled language, or let's say architecture, here in this sense. So you see, I do an initial call first, because the initial call involves a certain amount of overhead in time, and then I call it, and you see this is pretty quick here in this case, 5 milliseconds. But using number, and I will come to that in a second in a little bit more detail, you see I can get as fast as I'm getting with Julia as well. Because it's not only about integration, what we're using, the other typical prejudice that I'm facing when I'm arguing about Python or discussing it is that Python is too slow for many circumstances in many application scenarios. But you see, for certain things, using number as one example from continuum analytics makes things as fast as they are with other compiled languages or approaches as well. But to elaborate a little bit more on this point, because it's so important in the quant finance space, and my subtitle is Conquering the Analytics Space, and when we speak in finance about analytics, it's always about performance. And you see, even at these large institutions that are using Python strategically, like Bank of America Merrill Lynch, having more than 10 million lines of code in production of Python, they have, of course, their risk and derivatives analytics library implemented in C++, because it's fast, because they've been doing it since years and not only since yesterday. And for several reasons, this works pretty well, because it's efficient, you can easily interface and so forth. But I think many other smaller places, shops, hedge funds, for example, that start out anew, there is a realistic chance that they even want to implement their numerical analytical algorithms in Python. And there are many approaches to do that. Number is one, and I want to illustrate it again and to point to a few things that are worth mentioning, especially when it comes to financial algorithms. In financial algorithms, you more often than not see kind of nested loops. For Monte Carlo simulation, for binomial trees, trinomial trees, this is all about iterating, looping over certain numerical arrays. And here in this case, typically it's argued finance algorithms are loop heavy, is what I was saying. Python loops are so slow, therefore Python is too slow for finance. It's kind of a logical deduction, if you want to like. But I think it's not true for every use case. And more often than not, you find things where you can make the Python code as fast as with any other compiled language as well. Here in this case, just to illustrate two major points. One is about performance, the other is about memory efficiency. Consider a nested loop, which is quite typical. Again, for Monte Carlo simulation as the canonical case. This is just a way of counting and in a very costly, compute costly manner, the number of iterations that I'm doing here. You see here, it takes 10 seconds, roughly 11 seconds for 4 million loops only. So this is pretty slow, but again, you see here the cosine function, the logarithm function, these are all compute intensive operations, and that's the reason, or part of the reason why it takes so long. Of course, we have learned using NumPy, which is mainly implemented in C and Fortran, makes it much faster, actually. Here's the same result, less code, better readable, we all know what's going on here, in a fifth of a second. Much better, but there's always a price to pay. Here in this case, it's memory that you need. You see 4 million actually. What we're doing here, we occupy 32 megabytes of memory for this simple operation. And this is, of course, nothing you really want to do. Just to count something, to aggregate over something, and to occupy that much memory. When you think of like, let's say 10,000 derivatives products that have to be valued, and you every time occupy memory like that, then you're easily running out of memory, even if you have usual memory from kind of very realistic standards. Therefore, again, let's resort to number. Doing the same thing as before. We import number. We have seen it in Andy's talk as well. It's pretty simple. You import number. You call the JIT function on your pure Python function. No changes made. And now I call it for the first time to get rid of the overhead for the first time. And I evaluate the function then via time it. Here in Python, you see the result is the same. The speed is even 4 times faster than with NumPy. And it's as memory efficient as the Python implementation. So NumPy vectorization usually comes at a cost. You have to vectorize your things. And vectorization in this case means you need usually too much memory to implement this efficiently on a large scale. If you're doing research, a PhD research student and have some kind of small problem, that's fine. But when we think of larger hedge funds, big banks, this might be a deal broker to use Python. But you see here, number helps you not only to speed up the code, but even to be as memory efficient as you're used to with your C code or here the Python code, which is based on a nested loop. The other thing I like to mention why Python for Finance is that hardware-bound I/O typically comes at no cost. It's a default setting, so to say, with Python. There's only a small example. It's the only slide that I have here, but it illustrates it pretty well. I generate in memory on this MacBook here. I generate in memory a 1 gigabyte array. You see here the number of bytes within here. And I save it on disk. And what you see is kind of the in-memory generation. If the structure takes 7 seconds, writing it on the SSD drive in the MacBook Air takes a little bit more than 2 seconds. So we are almost at the limit of the speed that the hardware allows, which means roughly these 512 megabytes per second read and write speed. The other thing is that there's only little overhead involved. If we would write the same thing, not as a NumPy array natively on disk, but put it into, you name it, I think the worst case might be into MongoDB database or whatever, then you would probably see kind of an explosion of the data that you have to store, being not only a size burden, but also a performance burden when you have to write kind of 3 times the amount of original data. So this comes by default, so to say, for free when you're using Python for numerical analysis. And I was this year in January actually at the Supercomputing Center in Hilpisch at the conference, and this is kind of the main area where they are focusing at the moment their research, kind of the fastest I/O they can get their hands around. They are working closely with IBM to get as fast SSD disks as are available with the technology that are given today, and I think we will see many, many interesting applications in this regard in the future. What we've been working on recently, and we're using this mainly for kind of trainings that we do and for internal purposes with a few clients, the Python Quant platform, where we integrate IPython notebook. I don't want to go into that in more detail. I've provided all the links to that. You can look it up, where we kind of Docker container based allow you to install everything that you need to do interactive financial analytics on whatever kind of hardware you're using internally or in the cloud. Or whatever comes to your mind, even on your local machines, this works. There's a few things that are nice, but please follow the links. I want to focus here more on DX Analytics. There's a library for advanced derivatives analytics. And as you might know, I've been mentioning this Hello World example. Modern derivatives analytics started out with Black-Scholes in 1973. And back then it was kind of the holy grail to come up with kind of efficiently to evaluate closed form solutions. Not only from a theoretical point of view, that this is always kind of for mathematicians or finance people, it's kind of the nice thing to have a closed form solution. This is kind of, everybody's looking for that. But it was also due to the fact that machines like this, of course, haven't been around. I mean, Monte Carlo simulation itself was introduced to finance in an article by Boyle in 1977. I think this is already pretty early when it comes to computing power and compute architectures that we can get our hands on these days. But the idea was already there. But still, back then, and when I was a research student and did my PhD in math finance, there weren't the machines that even students today have available, where they go to DigitalOcean or to whatever cloud service provider and they can fire up like 100 instances in a few seconds and have the compute power of, let's say, smaller hedge funds or whatever. So this is easy today, but back then it was just, you had calculators. There were these Texas Instrument calculators. They came out with the Black-Scholes formula programmed into it, and this was innovation, And that's one of the reasons why you wanted to have back then and still even today, sometimes I get the impression, the closed form solutions. But times have changed, and banks are running hundreds, thousands of cores overnight, and not once a week or once a month. Every day, they're running all around the clock to do all these CVA, or let's say XVA calculations, as they call it today, where they have, for example, I have still the numbers in mind from a recent talk of Morgan Stanley, where they simulate 25,000 risk factors and risk manage, value 3 million positions that they have in their books on average per day. And you can imagine what this involves to simulate 25,000 risk factors overnight. So this is the reason, even although they are running like 100,000 of cores, some of them reaching almost 1 million, it still takes 6 hours, 7 hours, 8 hours. So that's one of the reasons why closed form solutions are still the instrument of choice that they want to use today to evaluate certain things. But DX Analytics, and this is one of the major premises, that's the reason why I'm a little bit arguing about this, is like founded on the premise, on the assumption that hardware is not a limiting factor. But what is DX Analytics all about? So if you want to go to the website dx-analytics.com, you see the documentation. I've also put up what I call an early bird repository. You can clone it from GitHub/Hilpisch, my username DX. You get all the code and 11 IPython notebooks that you can interactively execute. But the question is, why DX Analytics at all? First of all, we don't have that many financial libraries in the Python world. When we're speaking about the Python ecosystem, this is kind of the general Python ecosystem for science, data analytics, and so forth. But if you Google for financial libraries in Python, this is almost a dark spot. I mean, with the rise of Quantopian and the VC funding, I think we will see a little bit more, especially when it comes to backtesting. I mean, Zipline here and a few others, PyMC3 from Thomas Wiecki from this part, but PyMC3 again is a general Bayesian statistics library, is not especially dedicated to finance. I was recently approached by someone, one of my clients, who said, well, isn't there kind of any portfolio management optimization library in Python? I think there are a few things, there are wrappers, but pure Python stuff, this is really a rarity. So you have to look hard to find something at all. But with DX Analytics, I tried to start to bring advanced analytical financial capabilities to Python as well. Why? A brief history. I was arguing about all these closed form solutions, and the whole thing started back with the Bachelier thesis in 1900, via Black-Scholes, going to certain things here in American methods. You see the Boyle paper here in 1977, binomial option pricing 1979. What I caught my attention when I wrote my PhD thesis, and I fell in love with that, is the Harrison-Krebs-Pliska approach, which for the first time provided a general approach, where they said, well, we don't want to value a product. We want to have kind of a consistent general equilibrium model for all derivatives traded in a market. Be it as complex as I was describing it, even when we have 25,000 risk factors, we need kind of a theory that gives us instruments benchmarks where we can say this is a consistent approach to work in this market and to value all the instruments that are of importance here. Up until, I mean, when you think of the options world, this is one point I want to highlight here. And one of the reasons why Monte Carlo simulation, not only because it's so compute and memory intensive, wasn't that heavily used in the recent past, is it was pretty simple and pretty easy, and they started early out with it, to apply Monte Carlo valuation techniques to European exercise options. But for the American ones, which have been around as long as the European ones, there wasn't even an algorithm available to value these via Monte Carlo simulation. So this was a real obstacle. I mean, almost all options on stock indices, for example, in the US, are American options. There are a few exceptions, like options on the VIX, for certain reasons, are European exercise, but almost all options here in the US, as the name already suggests, are American options, and in the 90s, there haven't been any efficient methods available to value these options by Monte Carlo. But these days we have it, and we have the compute power to implement things that other researchers maybe 2 or even 3 decades ago weren't even able to think of, because they haven't had any idea how the future would evolve in this regard. This is more kind of the personal story where I said, well, during my PhD research, I fell in love with the approach of Harrison-Krebs-Pliska, which is so general. It's kind of, as the name suggests, it's a general valuation approach. When we started out with our company, it's almost 10 years ago, I tried from the beginning to implement something like that, but back then Python wasn't that well suited to do it. But over the years, I've been writing the book Derivatives Analytics with Python, now Python for Finance. With all the lessons learned from client work and so forth, I started out at the end of last year. I think it was in Dublin where I attended the conference, to put all things together and to write a new library. But because there's no business kind of model behind that, I have to work during my days from 5 at least, from 9 at least to 5. I wasn't able to put that much effort into it. But I want to present how far I came, at least. The quick start. What is it about? As a typical library, you import it, here in this case, as the X. The X stands for Derivatives Analytics. This is where the X comes from. What you need when you want to implement a general valuation approach is a risk-neutral discounting factor. That's the reason why the whole approach is sometimes called the risk-neutral valuation approach. You have your risk-neutral rate, and you discount all the contingent payoffs by this rate. The most simple case is to have a constant short rate, like in the Black-Scholes model. Black-Scholes assumes a constant short rate. We all know this is not true. Rates change over time, but for short maturity options, this is kind of an acceptable approximation, let's say. DX Analytics can more than that, but just to give you an insight and to have a simple example. What DX Analytics is based on is kind of what is kind of usual, not only for Python or what we are doing, to define market environments by data. So there's a market environment class where you, in simple words, collect all the data that you need to implement a valuation. Details are not that important, but you can imagine you need kind of a starting date, you need a maturity date. When you want to model a risk factor, you need an initial value, volatility for the geometric Brownian motion. Typically, instruments have a currency that they are denominated on. And when you want to do a Monte Carlo simulation, you need also an assumption for the discretization, be it weekly, monthly, daily, or whatever. And you need the number of paths that you want to simulate, 1,000, 10,000, 100,000. So, and the market environment does not more nor less than to collect all the data. And we can pass this object to the other objects of relevance. And they can take out from there what they need to function, to work. And here you see, I define a new object. This is a simulation object for the first risk factor. This is a general risk factor. You can think of it like a stock price, which moves randomly over time. I only give it a name and pass on the market environment, and then I have another instantiated object. When we use this, for example, we can get instrument values out of this object. And here I visualize 10 simulated paths, just to give you an impression. For those of you who have ever worked with Monte Carlo simulation, this is nothing new. But if you've never seen it, this might look like 10 different paths for something you can see in the Wall Street Journal or any other financial charts you might have seen in the recent past. So this is what we're doing. We start with a certain value and we simulate the future. We don't say we know how the future is. We just say, well, we know the initial value. We have an assumption about the volatility. And these are possible outcomes. And in the end, we want to average over the possible outcomes and discount stuff back to come up with present values and other things. What we do here is kind of define a second object, and this brings already in the generality in a sense. Black-Scholes is based on a single risk factor and on the modeling of a single option. Nothing more, nothing less. One risk factor, one option. What we do here is kind of model at the same time, simultaneously, a second risk factor that we also simulate. You see, this is assumed to have a higher volatility. Here we go up to 250 from 100. This picture, here you see the highest path, the maximum here is roughly about 150. So much more volatility, we have a larger spread of the values. The next thing is we define our derivatives based on these risk factors. Same thing, we need a market environment. This market environment, which collects the data, gets passed to another class. Here in this case is the valuation class for Monte Carlo simulation, American exercise, and a single risk factor. What we define is the payoff. You see here, if you're used to this Python syntax of NumPy, we can freely define the payoff of our option. We are not restricted to kind of a European standard plain vanilla option. These can have like Asian features, look-back features, and so forth. And once we have defined that, we can start valuing it. So even if this is kind of something where there exists no closed formula, I was arguing so long about the closed formula of Black-Scholes. For an American option on such an underlying risk factor, there is no closed formula available, but our numerical approach allows us to work with it as if there was a closed formula. In this case, I call the method present value, get back the present value of the option. I call the delta, get back the delta of the option. I call the vega, and get back the vega of the option. I don't have time to explain these things, either you know them or not, but be assured these are kind of very important statistics that you need for trading, risk management, managing and valuing, pricing options of any kind. Now we define the second one. Same thing, but this time European exercise. Same thing, present value, delta, vega. Now we have a call. You see the delta is positive, before it was negative. This is kind of a technical thing, we need to add information about the models we use. We can now define, and now comes the specialty of the analytics, we can start defining derivatives positions, which involve a little bit more meta information. For example, in what quantity do we have it in the portfolio? Usually, it's not that you have, if you have 10 derivatives, that you have always a quantity of 1. You have 10 of these, 15 of these, 20 of the other ones, and some are short, some are long, and so forth. So we can define here derivatives positions, and these get passed to a portfolio. But before we can pass these to a portfolio, we need to do some kind of meta or general assumptions for the valuation. We have to tell the portfolio class what kind of risk factors are important, are they correlated or not. If they are correlated, we have to pass correlations in here, and we define the positions. And in the end, there are also kind of general assumptions about the valuation. You've seen we have had valuation objects that have their own paths and frequency assumptions and so forth. But when I want to do a consistent integrated valuation, I need to make sure that I have unified assumptions for every single valuation object, and this happens here with the valuation environment. And now it's only this code to define my portfolio, and this is kind of already a complex beast object containing lots of information, lots of assumption, market data, and so forth. But in the end, it's pretty valid to work with it. For example, now, when I'm interested in only, so to say, the values of my portfolio, I can do a valuation on a consistent basis. All the 2 risk factors get simulated. I get values for my two positions in here. The one is an American single option, the other one is a European, and so forth. But these can be really complex beasts that are contained in here. But just to illustrate how this all works, you've seen we've started with the risk factors. Given our market environment, this typically is delivered by Bloomberg, Thomson Reuters, or wherever you get your data from. You put the data in the market environment, you pass this to the risk factors. Maybe you have a calibration step where you calibrate the risk, the parameters of the models to the market data. Next step, you define your derivatives positions, and in the last step, you define your portfolio. And once you have defined this, you can do a couple of things, like here, getting the values out of the portfolio, or this is more compute intensive, calling the get statistics method. This provides also vega and deltas on a portfolio level. Here again, you see the one is a put option with a negative position delta. The other one is a call option with a positive position delta. You see all the totals over here, and so you can get as much information out of this object as you desire in the end. What you can also do, and this is also important from a risk management perspective, you can shock certain parameter values. Here, for example, I say for all the risk factors in the portfolio, I want to get a portfolio risk report. And this, for example, says that the ones here, these are percentage assumptions, that we say, well, this risk factor starts with an initial value of 100, and you see the portfolio value is 35.96. And what happens if we change this assumption that, to the case where the initial value is 90 or 80 or 110 or 120, and you see you get relative ceteris paribus values, the sensitivities of your whole portfolio value, given the changes in your single risk factor parameters. The same can be done, for example, with the volatility values. Here I have changed the step size so you get a finer grid of different parameter values, but again you see we start with the same value, 35.96. And what happens if we increase the volatility by 5%, which means by 1 point? You see the value increases in this case by roughly 50 cents in this case. So you can get very detailed information out of what we have defined now, a derivatives portfolio. But this is still pretty simple. But again, I would be more than happy if you would point me to any kind of library that follows a similar approach, be it in C++ or wherever. Even the most popular one, Quant, follows a completely different approach. So I would be more than happy if someone could point me to any place which follows a similar thing. Because this, from my experience, is only done on really large scales by the large institutions in the world. And in these cases, not in the front office, for front office analytics, trading and pricing, but only in the back office for XVA, mainly for XVA, VRR calculations and so forth, for the whole portfolio. And this is what is one of my motivations for DX Analytics, not only to bring financial analytics to Python, but to bring this general back office simulation and risk management approach to front office analytics as well. To point only to one thing that is a real mess, and if you speak to people who are not traders and who are not desk heads and so forth, but who are in risk, compliance or whatever, they are trading products based on the same underlying, let's say the S&P 500, but you will find in a single bank maybe 50 different modelings of the risk factor, in a sense that it's all but consistent. And in the end, a bank should have kind of a position, at least on the major assumptions, what makes the stochastics of one of the main risk factors. But again, you will see many, many different modelings of the same market beast, so to say, when you go to reality. But let's make a realistic example of DX analytics, but this is not realistic from a bank standpoint, but to make it a little bit more complex. What we do is we model value and risk manage, so to say, a quite complex derivatives analytics portfolio. The example has the following main characteristics or the following main assumptions. A portfolio is valued over 2 years. We now have a stochastic short rate, which could be calibrated to a term structure of whatever kind. We are now simulating 250 correlated risk factors, which we recruit out of 3 modeling types. The one is geometric Brownian motion, the other one is a jump diffusion, and the next one is stochastic volatility, all included in DX analytics. We define 1,000 derivatives based on these risk factors. Call and put option, European and American exercise, random maturities. So we are still not at the Morgan Stanley level, for example, but again, this is pretty hard with, if you go to any kind of commercial vendor who sells derivatives analytics software and you ask them for this, it's pretty hard for them to model this in even a remotely efficient way. What we do, and this is due to the fact that I've been doing this on my MacBook here, it's not on a cluster, it's not on a big machine or whatever. What you see right now is done here on the MacBook, actually. I only do monthly frequency, which means we have 26 points in time, or 20, yeah, with the starting and the end dates, we have 25 points in time. And for 1,000 paths, but still we have 250 risk factors and also American exercise where we have to calculate the optimal exercise points over time. Let us start with a stochastic short rate. I don't go into details. Again, this is the market environment for our stochastics, given our assumptions for the short rate model. Just to illustrate, this starts by 0.5%, and we assume a long-term mean which is much higher. I think here the long-term mean is assumed to be 3%. And you see here is kind of the term structure illustrated in our stochastic simulation of the short rate process. We have multiple risk factors. What I do here, I collect data in a market environment which comprises all the things that we need for the 3 models that we allow. So be it a geometric Brownian motion, jump diffusion, or stochastic volatility model. Here you see we add the jump diffusion parameters, the stochastic volatility parameters. These are all assumptions. They may not make any sense. They're just typical ones in a certain sense. But you could also use any kind of other assumption set. The valuation environment, you see here 1,000 paths, monthly frequency, and our discount curve object that we do in here. And now we go on and add the valuation environment to our overall environment. What we do here is kind of, because I didn't want to type it all down, via looping, we generate 250 risk factors where we randomize the initial value of every risk factor, where we randomize also the volatility factor for every risk factor that we have in our portfolio. The next step is that we randomly chose correlations between the first risk factor and all the other ones. Of course, this does have to make sense. Therefore, I'm pretty, let's say, conservative with my assumptions because the matrices, the Cholesky one, given our linear algebra implementations, have to make sense, have to exist in order for us to simulate something sensible here. Now we model the options. Certain additional assumptions. Here in this case, we randomize over majorities, actually, so that we have kind of certain strips of options per majority. The next step is to model the portfolio. Here you see the 1,000 derivatives positions modeled. The randomization here is that we either choose American single option, which is a call in this case, or a European single option, which is a put in this case. So we have many random factors in there. In the end, we end up with 250 risk factors and 1,000 positions defined on that. Now we can go on with the portfolio definition, which is actually the same as before. We path our mainly dictionaries to this class to instantiate a derivatives portfolio object. And you see here, this is the correlation matrix, now composed of 250 times, sorry, this is multi-touch MacBook, sorry about that. but you get the point. This is kind of our market, our correlation structure. Most of the things are zero in this case because we only have correlations via the first risk factor in order to come up with a existence Cholesky matrix in the end. Now we can value this, and again, this is all run on my computer, on my machine here, and I see the wall time is roughly 10 minutes. I mean, it's kind of a realistic portfolio already, but I'm able, to model this with DX Analytics. It's pure Python. There's no Thython or anything else, I know. It beeped already, thanks for the hint. In there, it's sequential calculation mainly. And again, I'm able to model it and I'm able to evaluate it, even if it's only 1,000 pass. Typically for a realistic application you would have much more pass, maybe 100,000 or even 500,000, but it runs on my local machine. I can do advanced derivatives analytics with 1,000 options in my portfolio, even on a local machine by using the DX Analytics library. And here you see the results. Sorry, I'm simply not able to navigate this highly sophisticated thing. I don't know what it does. I'm not sensitive enough. But you see, this is the results table. The positions are simply numbered from 0 to 999. You see the quantity, which is randomized. You see the different types and so forth. You see the value, the position vega, and the position delta actually over the whole portfolio of things that we have in here. You can also do, of course, the risk analysis. This involves, for example, and this is the beauty or one of the beautiful aspects of this approach, we not only get a point estimate, the mean, the average, we get the full distribution of the portfolio for this thing. Very important information to calculate, the XVAs, VAR, and so forth. We can also generate out of this statistics like certain percentiles, minimum values, maximum values, mean, standard deviation, and so forth. We can shock this, and this is done in a kind of lazy way, in a sense that only those things are re-evaluated that are kind of directly impacted by my shock, in a sense. So you see here, when I shock one single risk factor with regard to the initial value, for example, this takes only 1 minute and not like 10 minutes or whatever for 4 different risk factors. Though this is lazy calculation, or in some cases you would say this is a directed graph approach where we know what is impacted by our assumption and we can accordingly act to that. Visualization of selected results, of course, you get the full view on what you've been doing. You see the position deltas distributed as you would see it. On the positive side of the position deltas, we have the American options, which are differently distributed, and on the negative side, we have the European put options. You see the negative values for these. And last but not least, an illustration of the consistency in simulation. You can, of course, visualize every single risk factors. I have taken out here 3 randomly, so to say, the first 3 ones, and you see different starting points, different volatilities. One is with jumps, the other is not. So you have a full view and full information of what is going on in here. That's actually all about DX Analytics. I want to end with a little bit of marketing. If you are interested in Python for Quant Finance, want to get a start or want to know more, of course there are books. There are 2 books out at the moment written by others, 2 books by myself. The one will be out in print is Python for Finance by O'Reilly this December. You can buy the ebook version already since quite a while. The next one, Derivatives Analytics with Python, will come out in 2015. Will be published by Wiley Finance. This is a quant book. The other one is more a Python book, I must say. The O'Reilly one teaches Python. This teaches finance, actually. There are many meetups that we do. I've shown this in London and New York. Our for Python conference, I have also mentioned before, will take place for the 2nd time and probably for the first time in Asia in Q1. And yeah, here you see the site again. I think I've been showing it. And my final thoughts are actually, I wish for Python in the future. I think this is not only with regard to finance, it's with regard to analytics and data analytics in general, to become the clue language and platform for data analytics, financial analytics, derivatives, risk, development efforts, and performance technologies. And again, my discussion yesterday with this potential client, this hedge fund, large hedge fund, I'm always arguing about this, that Python, from my point of view, is the only platform technology going forward will provide you with the flexibility to accomplish or to come over all challenges that the market will probably provide you. And that's already it. Thanks for listening and happy to take your questions.